recording now, I think. Yeah.
Okay, Dr. Wani, good morning to Dr. Wani. Today we are presenting our
Dr. Chan.
Dr. Chan, yes. So they are presenting lab spring. Okay. So I will start the present. So can you all see the screen? Okay.
Yes.
So okay, this is the 4 wire I use. This 50 cm, 40 cm, 60 cm, 70 cm. So after I roll the wire, so the length become 5.6 cm, 2.1 cm, 3.2 cm, 4.7 cm, and 5.6 centimeter. So yes. So this is for 30 cm wire, which is 4.6 cm spring. I use the hand sanitizer. So here's the top. So for second wire, I use M. This is second wire, second spring. So this is third spring. Okay. So this is
Sorry.
fourth spring. Okay. So yeah, this is the result. So here is after the elongation. So the elongation is this elongation is 1.4 cm. This elongation is 2.3. This is also 2.3. This is also 2.4. So the conclusion is, my conclusion is, if the longer the spring, the longer the elongation that can gain. So the lower the strain. So yeah. So for the graph diagram, strain and stress diagram. So we have two region. Yes. Which is elastic region. Here is elastic region, and here is plastic region. So at the elastic region, the Hooke's law is obeyed. There is stress and strain are directly proportional to each other, which is Hooke's law is a law of physics that states that the force needed to extend or compress a spring by some distance scales linearly with respect to that distance. Is F equal to Kx, where K is constant factor characteristic of the spring. So for the elastic region, here straight line obey the Hooke's law. So here is the yield strength. the lekuk there. So this this is the yield point. So what is yield point? Yield point is the maximum point for the spring to 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 positional to to become to return to its normal state. Yes. So as the what we call, we stretch the spring. So
The extension.
the extension of spring. As long as we extend the spring, yield point is the maximum point where we can extend the spring and we pass it and it become normal state. So if we exceed the yield point, the spring cannot become to the normal state. So yang modulus is basically it's the slope. So rise here, the rise over run. So basically run is x, strain, rise is stress. Okay. So the plastic region. Here is the plastic region. Plastic region is where applying a force, the body undergoes a permanent deformation. So after here, there is a permanent deformation, where is deformation to the normal state of spring cannot be done. So the spring static on its condition where it is extend. So yes. So that's all from me. Thank you.
Okay, thank you, Afi. Wow, yours was so complete, yeah.
Yeah. Dah ni stress strain.
Yeah.
Yeah. So for the stress is a quantity that describe the distribution of internal forces within a body. So how we know the stress is force equal to area. So force we apply on the spring, and area is the surface area of the spring,
Yeah.
So for the strain is a quantity that describe the deformation that occur within a body. So how we know a body? Strain is elongation of the spring over the initial length of spring. So that's it.
Okay. So now I'm going to try to. You guys can see. Oh, cause initially I thought the discussion will be held tomorrow, but it's okay. Hafi is like almost explained it all already. Very good. So we almost are all clear. So this is, you guys can see my face. Did I mute?
Yes.
Okay. You guys can hear the sound.
No, cannot.
Okay.
No.
So I curl my spring. So I'm going to fix one weight only. So I measured the measuring scale. So it's 200 grams. This is the 7 cm spring. So now it extends. I'm measuring the final length. So it's 9 cm. So it extends for like 2 cm. So I'm doing 3 readings. So the second reading is at 8.5 cm. And the third reading also 8.5. For this spring, it is the 3.6 cm. After elongation, it's 5 cm. So the extension for it, it's 1.5 cm. Again, I measure 3 readings and take the average of it. So this is the second shortest one, which is 2.5 cm. I measure the length of the spring, not the length of the wire. So for this one, my first final length was 3.4, 3 and 3.2. So the extension for it is like 1 point something for the extension cm. So this is the weight of my pencil case. And now it's the shortest spring. Like the shape is very weird, but it's the shortest one. And it's 1 cm for the initial length. So I measured its extension. Actually, the long ruler at the back, I can't see it very well, so I'm using my short ruler. So it's 1.1, 1.2, and 1.1. So the extension is just like very little. So that's all for my experiment. Yes. X.
Okay, good.
Yeah. So next, you guys want to go first? What? Any question for my experiment?
Let me
No?
try to present.
Sorry?
Can you see my screen?
Not yet.
What about now?
Still haven't. Oh, by the way, is my experiment clear just now?
Yes.
Any question about my experiment?
No.
Okay. So you guys did do 3 readings, right?
Yes.
Okay,
Yes.
good.
So here are the materials I'm going. Can you see my screen?
Yeah.
Oh, okay. So I'm going to be using 3 different weights. Here it's 270 grams, 250 grams, 270 grams, and here it's 170. So for the first one, for the longer, for the first string, for the longer one, I measured the diameter here, so never mind.
So where did you hang? Oh, okay. Sorry. Continue.
Okay, so here I'm measuring the initial length of the string. It's 2.5 centimeter. And then I placed for the second string, it's 1.8 centimeter. Okay, so now I'm going to put the weight on. Here it's 170 grams. So the extension was 2.5 for the first string, which means the extension was 0 centimeter. I mean, sorry, it's not the extension, because for the first weight it didn't show any change, so 0 extension. For the second one, This one, it showed 0.3 centimeter extension. And this is the third one. It showed 0.9 centimeter extension. For the second string, also 0 extension. I think because the weight was too small, that's why. In here, it's 0.5 centimeter extension. For the last one, it is 0.3 centimeters. And that's all. Thank you. I'm just going to explain briefly about stress strain graph, stress strain curve, sorry. It basically gives the relationship between stress and strain, and it is obtained gradually by applying load and measuring deformation, from which the stress and strain can be determined. We have few properties such as strength, toughness, elasticity, and strain energy. That's all. Thank you. Do you have any questions? Okay.
Okay, so my turn to present.
Wait,
Share
wait.
my. Yeah, okay.
Yeah. So nurse, you're using different weight, right?
Yeah.
So you did take 3 readings also, right?
Yeah.
Okay.
Okay, so I'll present now. Okay, so I share my screen here. Wait, where to share? Wait, give me a second. Suddenly forget how to share screen. Oh, okay. Sorry. Okay, you guys can see my screen now, huh? This one. Yes, right? Yes, huh?
Yeah.
Okay, so I start lah.
Right.
So this is my experiment. I get 2 wire. Then, wait then I open it. Sorry, I thought I need to include this procedure. Then I open it. Then I measure it. Become 30 cm, 70 cm, 40 cm, and 60 cm. Yeah. So I use measuring tape to measure it. Then measure. Okay. Then I use a scissors to make a marker there. Then use a plier to cut it. The face a bit. Okay. Okay, so I cut it lah. Then I use a screwdriver to bend it, anchor it, everything lah. Then my spring will become, this one is 30, how much 30, 40, 60, and 70. 30, 40, 60, and 70. Then I curl it with the size of screwdriver lah. Then the diameter here, no, not the diameter. The length of spring is 1.5, 2.1, 3.5, and 5.0. The diameter is about 0.7 cm. Yeah. So I did 2 parts lah actually. One part is different length. For the different length of spring, I put I measure the length of spring first before I put the load. Then this load is about 500 gram, which is 5 Newton. Then after I place the load, I use the measuring tape to measure it again. Then repeat it 3 times, this procedure, to get the average reading of the after reading. Then after I lift the load, I realized that the spring will return to its original length, which is its original length. Yeah, so I repeat it with different length of spring. This one is about 5 cm one. I didn't put everything inside lah, because it's kinda boring. Yeah, so I measure it, I put the load. Okay, I put the load. Okay, I put the load, then I measure the elongation, then repeat it 3 times lah. Yeah. So same, repeat. So part 2 I did for one spring, then I verifying the mass. So the spring I take is about 5 cm one. Then this load is about 500 grams, same as just now, 5 Newton. Then I measure the before reading. I measure before reading first, then I put the load, then I measure the elongation. Then repeat 3 times. This one is for 1 kg, which is 10 Newton. Yeah, I measure it again, then repeat. Okay, then this one is 15 Newton. I feel the water below lah. Yeah. Then after it, this is my table. The table I get is this one. If you guys can see lah. So I did 2 table. This is my reading lah. So I realized that if I increase my length of spring, the extension is actually getting bigger. Which obey the Hooke's law lah. So the longer the spring, the longer the length of spring, the longer the extension. Yeah. Then table 2 is I verifying the weight. So I'm trying to find the yield point, but I think I can't because I can't get the accurate reading of the yield point. So I'm just increasing the weight of load, and I discover the extension of the wire lah. So if the weight of the load increase, the extension will become larger. Once it reach the yield point, I think my spring will can't return to its original position. Yeah, so basically that's all for my experiment. Any problems? Am I clear?
Problem no lah, but then for the scissor part, right? Is it actually you want to cut with scissor, but then you can't cut with scissor?
Yes. I'm trying to cut with scissors, then I realized I only can make a marker but cannot cut it all. So I use a
I spoiled 2 scissors because of that one. Because I spoiled 2 scissors.
yeah. So that's all for my experiment lah. Then maybe I can explain a bit about spring. We did discussion here together, right? Or tomorrow?
We did discussion here together, or you guys want tomorrow?
I think you don't know.
I think better now because Happy already did his own discussion.
Ready
Okay.
now?
Sorry?
You are
Yeah, I already discussed.
Discuss.
Yeah. You already discussed just now.
I
So
leave it.
basically, just now Hafi have discussed the stress strain graph and Young modulus and
Hooke's law.
the
Yes, sir.
no he didn't mention about Hooke's law.
Ah, okay.
That's the stress strain graph.
So
Yeah.
maybe I can add something.
Yeah, just add.
So maybe I add the characteristic of spring lah. So spring is an object that can deform by force, then it will return to its original shape after the force is removed. So if we put some load, then the spring doesn't overload the yield point, the spring will return to its original position. So it's like elastic deformation, but after the spring over the load, it will broken lah, like it can't return to its original shape, then it's permanent and irreversible, so it will reach the plastic deformation lah. Before the yield point, it will reversible return to its original position, and it's not permanent one. Yeah, one of the characteristics of a spring.
So that's about Hooke's law, right?
Yeah,
Because spring. Yeah. Because basically everything that has elasticity needs to obey Hooke's law. If it reach its limit, then the spring will be like when it does not obey Hooke's law, the graph will not be directly proportional. Means it is spoiled.
Yeah.
Because it reached its extension limit. Spring limit, yes.
Yeah. Then I also found something about elastic potential energy lah. It's a potential energy that is stored at spring when the spring is trying to try to compress or try to stretch. So it's elastic potential energy lah. Then the formula of elastic potential energy is US is equal to elastic potential energy equal to half kx squared. The k is about spring constant, the x is elongation. Yeah, so if you want to draw the graph, if this is the force, then this is the extension. We draw the graph lah. Then this line will become the spring constant, but the area will become the elastic potential energy if you want to draw the graph. Yeah.
That's the energy, right?
Hmm?
That's the energy, right? The U,
Energy.
right?
Yeah, US. US. Yeah.
Oh, so from what we can conclude from this, like from the four of us experiments, we can know that the longer it is, the longer the spring, the longer the extension. Am I right?
Yeah.
Okay. And for the mass, the heavier it is, the longer the extension.
Yeah.
Yeah, so that's for our experiment conclusions, right?
Yeah.
Like
But
for what we
once,
can conclude from the four experiment, right?
but once the mass overload, like over the yield point, it can return to its original position.
Yeah. Oh, so anyone got exceed the limit of the spring?
No. I was trying to find, but I can't find the specific mass.
Because if they exceed the limit of the spring, the what we call the result there for the table should be put blank. Because we cannot, because it doesn't obey Hooke's law, so it needs to be blank, like blank. Because yeah. So everyone clear about our experiment? Since the objective is just measure, like we need to know stress strain graph and the different length on spring, right? That yeah. Okay, so I think that's all for our experiment. Anything to add on?
So those you have anything to add on? No. I think that's all.
If everyone is okay?
Yeah.
Nothing to add on. Everyone's clear about our experiment.
Yes.
Yeah.
Okay, I think so. Since we are clear, we can end our discussion and discussion for spring, for our last lab. Spring. All right, thank you guys.
Okay,
I think can.
so thank you. So I'll start recording right now. Thank you, doctor,
Yeah.
for what? Yeah.
Yeah, I can stop recording already. Thank you.
Wait, let me think. Here. Okay.
Kelly.